Okay, I'd like to talk about a little bit of review from last week. Here's our account. We've got our amount total depends on our principal, the initial amount times, this is a growth rate. This deals with us growing money. And remember, this is the full-fledged, if it's more than just annual compounding, like quarterly compounding, we have to adjust. If we have a compounding period more than once a year, we have to adjust our annual rate and divide it by how many times per year that we are going to compound the interest. So N is 4 for quarterly, 12 for monthly, 2 for every 6 months, okay? 365 for daily, okay? And then this helps us figure out how many times we compound it. If N is 4, then 4 goes up here, and this is really for a yearly amount. Okay, so if we've got an annual rate of, let's say, a certain percent, we adjust that in decimal form, divide it, let's say, by 4 for quarterly, and then we put 4 up here because it's 4 times per year, and we plug in years for T. Okay, all right, but the main thing that we want out of our exponent is it needs to reflect how many times we compound the interest. So if we're going to compound interest for 10 years and it's quarterly, well, that'd be 4 times 10 would be 40. Okay, this exercise we had last week was when we had this T represents in years, and we were given a table where 3 months, 6 months. Well, this is obviously a fraction of a year, so you had a couple choices. You know, when we plug in 5%, which is 0.05 annual rate, and we divide it by 4 because we compound our interest 4 times a year every quarter, we raise this principal times this growth rate to the 4 times T. Well, we can either do one, adjust T as far as 3 months is 1/4 of a year, 6 months is 1/2 of a year, and 9 months is 3/4, right? Every 3 months is a quarter, so that's be 3/4, and plug that in. Okay, or you could do this, just plug in 4 is your 0.05 over 4 over N, and then just put in here. But you obviously recognize that this is in quarters, okay? So when you figure out, if you do this method, if you plug in 1, 2, 3, you're not adjusting for 4 quarters a year. This is in quarters, okay? So 1/4 would be the 3 months, 2 quarters is the 6 months, and that way it took care of these months, but we have to adjust for that later. Okay, if you look at your table from your in your calculator and time to double said 56, well, remember what that represents, 56 quarters. Now you have to adjust, before you adjusted for things by multiplying by 4. Here, where this is in quarters, we'd have to adjust for this and divide by 4 to get, there's 4 quarters in a year. 56 quarters represents 14 years. So either way, understand what your exponent means. You need it. This represents how many times you're going to compound. If you don't put the quarters times the NT here, it represents you're just dealing in every 3 periods of quarters of a year. All right, we talked about we finished up the concept of E, and if we didn't, part of your exercise was you have this $1 that gets 100%. Well, 100% adjusted in decimal form is 1. Okay, and we started off putting a 1 down here and a 1 up here for N. Okay. So 1 plus 1 is 2 to the first power is 2. And then we divided, we continue to make this smaller, but also make our exponent bigger. Make N 10, 1 over 10, 10 times a year, but we're going to raise it, obviously, figure this interest rate 10 times a year here too. Okay, 1 divided by 100 times, we're going to figure out our interest 100 times a year. So we divide 1 by 100. But also raise it to 100, and we keep getting this denominator bigger and also raise it to the same amount, so it's almost a check and balance. If you keep taking this to huge amounts, like 1 plus 1 over a million, but raise this number to a millionth power, it eventually hits a limit of 2.71828182846. That's E, okay? And that basically is the concept of this being 1 over infinity to infinity. This means continuous compounding. Okay, if you raise 1 plus 1 over infinity, we're going to, every nanosecond, we're going to figure out interest, and we're also going to compound at every nanosecond. Okay, so we divide our interest rate by infinity, but raise it to infinity. It eventually hits this limit here. That's E. That's the number E on your calculator. Okay. All right. Let's go with this. Okay. Now that we've got this concept, since 1 plus, let me blow this up here. Okay. Since 1 plus 1 over infinity to infinity is E, this represents interest compounded continuously, right? We divide this annual rate up into infinite periods, but we raise it, we figure out our interest at infinite times, okay? So here's our formula. I call it PERT, like I don't know if it's still out, it used to be a shampoo called PERT. We're going to take our initial principal, and then our growth rate basically is this E. This right here represents continuous interest, right? We divide our annual rate into infinite periods, but raise it, but we compound the interest infinite times. So that's E. And we'll raise E to the interest rate in decimal form and multiply it times the time period. So here's our exponent, is RT. All right, so take a look. We'll take $10,000 as our principal, initial investment. It's continuous compounding, round-the-clock compounding. 3.75% in annual rate, but continuous compounding. And we want it for 10 years. So my amount in 10 years is going to be $10,000 is P times E, which represents continuous compounding, to the RT, and my rate, move the decimal 2 places to the left, 0.0375 times 10. Okay? And that would make this basically this 10 moves this decimal point over there. Anyway, you plug that in your calculator and you get $14,549.91 basically, okay? All right, now that's the type of problem you need to deal with. Okay, now Joe buys a car. Here's another problem we're going to deal with depreciation. We've been doing growth. Let's talk about depreciation. Remember, decay rates are not 1 plus, but they're 1 minus your rate, an annual rate, okay, in decimal form. So Joe buys a car at $20,000. It depreciates at 15% annually per year, okay? What will be its value in 5 years, okay? So we're just dealing with annual rates, no compounding quarterly or anything. It's just an annual depreciation rate. So my decay rate is 1 minus R, unlike a growth rate, which is 1 plus R, okay? 1 minus R, okay, becomes 1 minus this 15% in decimal form, move the decimal 2 places to the left, is 0.15, is 0.85. So every year we multiply this 20,000 times 0.85 times 0.85 till finally after 5 times, it's 20,000 times 0.85 to the 5th power, okay? And that'll give us your car, and this is pretty accurate, it's going to be about worth $8,874 after 5 years if you paid $20,000 for it. Okay, I'd pull that 15% out of a hat, but I'm pretty sure that's pretty close because your car value is worth about half after 3 years. So this is pretty accurate. Okay, so here's another problem that we've kind of dealt with. When will the car be worth half its original value? And we've dealt with these doubling and tripling. It's the same thing, except this time it's half. I don't even need to I could put $20,000 in here. When does it equal $10,000, correct? But it's just basically, hey, when does my initial amount become half the amount? And all we have to do is what? Divide both sides by that A. Those A's will cancel out and we're left with 1/2. If you had 20,000 and 10,000 and you divided 10,000 by 20,000, divided both sides by 20,000, you would get 1/2. So you don't even need to plug in a value. The value, you just plug in an amount. Just plug in the variable. A becomes 1/2 A. Divide both sides by A. The A's cancel out. I'm left with 1/2 equals what? 0.85 to the T. We need to solve for that. So remember, take the log or common log or natural log of both sides. So when I do this, I've kind of skipped a step. When I took the log of both sides, I moved the exponent from here down to here. And now T is no longer an exponent. It's just this variable we can solve for. Okay, so T times this, log 8.85, equals this. So I'm going to divide. I want to get T by itself. I divide both sides by log of 0.85. I kind of skipping the steps, but you should know what's going on algebraically. Okay, so notice I divided both sides by the log of 0.85. So I have basically T is going to equal log of 0.5 over log of 0.85, okay? So again, whether you're growing or decaying, if you want the time, you take the log of whatever you're doubling or tripling, or this time halving, and divide it by the log of the growth or decay rate, and you get the time, which is 4.265 years. So a little over 4 years, this car at this 15% depreciation is worth half its value, and after into 5, it's worth less than half, okay? One last thing. Okay, we just kind of talked about this again. So here's amount to double, triple. Again, you take an amount, we're going to triple, just cancel out the A's. Again, what are we going to want to do? Here's where, oh, this is one thing I want to show you briefly. Okay, now I've got, this is what I have I want amount to triple, and it's 10,000 count at 3.5% annual rate compounded quarterly. So I've got my growth rate of 1 plus 0.035. The rate adjusted in decimal form divided by 4 to the 4t, okay? 4 times a year, okay? What's the time for this to triple? So I just plug A and 3A. The A's will cancel out because you just divide both sides by A. And I get 3 equals this right here, whatever this amount is, 1.01 plus 0.035 over 4 to the 4t, okay? So again, we take the log of both sides, and notice my exponent, which is 4t, is allowed to come down and no longer be an exponent. That's why we do this. I divide the log of 3 by the log of this interest rate, and that equals not just t this time, it equals 4t, okay? And finally, so this is all I have to do now to actually solve for t is what? This is just divide both sides by t. So I have this amount here. T is this log of 3 over log of 1 plus 0.035 over 4, this whole thing, and we divide both sides by 4. So just an extra step here, okay? Last thing, talking about a nominal rate. That's just basically when you have an 8% annual rate, but you're going to compound it quarterly, we're going to take that 8% and divide it by 4 and get 2% per quarter. Whenever you have an annual rate that's going to eventually be divided up, before it's divided up, we call that the nominal rate, okay? It's 2% per quarter, 2% compounded quarterly, but the nominal rate was the annual rate before you split it up into its periods of monthly or quarterly, okay? So 8% is the nominal rate. That's all I have. I'll introduce a couple new things tomorrow, but the big thing for the lesson was the continuous interest, the PERT, the halving. Those are the type of problems. These problems are very repetitive in nature, okay? All right.